1, 2, cool. Hello everyone. So as David says, I worked on the CTF, and now I'm doing this talk, and I also work for Tor project. So this is why I'm doing this Tor Onion Services talk. But first of all, I just want to know who knows what Tor is. Show of hand. Okay, basically everyone. Now, who uses Tor, daily? Show of hands. Okay, who runs a relay? Show of hands. 1, 2, 3, 4, 5. Okay, so I have some hot sauce here, and I would like to give the hot sauce to the fastest Tor operator. So the 5 of you, come see me at the end, and then we do this kind of a contest of who has the faster relay. And then you get a nice hot sauce. It's amazing. All right, so deep dive into Tor Onion Services. If some of you were at OPE last year, this is the Onion Services talk, but a year has passed in between, so I've updated the slides. We've made humongous amount of progress in terms of development, so we're going to go through it. But this is fairly technical. I'm going to go through what is Tor Onion Services, and then what happened with the next generation Onion Services. What's the attacks and the breakage between. So first of all, I'm just going to do a small overview about what Tor is. I do work for Tor. I'm a full-time employee for the Tor project. And it's a nonprofit organization based in the US. It used to be in Boston, now it moved to Seattle. We basically do online privacy, anonymity, lots of research. We are basically operating around $3 million budget, all based on grants, donations, and some funding from, as you know, different governments. It's a huge, kind of a huge and diverse community. I think I have a slide for that. Oh, there you go. So the bigger outer layer of the onion, we have around 7,000 relay operators around the world, 3,000 bridges. I'm not going to get into bridge, but if you have more questions, feel free to ask them after the talk. So this will be a bridge-free talk. We have a lot of applications, actually. We have Tor Browser, Tor Messenger, Tor Birdie for Thunderbird. We have the Tor, little T-Tor, we call it. And we have many other things around it. And it adds up to around 50 different projects. So right now, at all time, in the Tor network, it's 2 million users. So the thing with when you build an anonymity network, you cannot really measure who is on the network and when they log in or whatnot. So this 2 million is an estimate, and it's at all times. So we don't know if it's 2 million users that just come back or just 2 million users it happens to be right now. But we do know that there's around 100 and 150 million unique download of Tor browser every year. So whatever you can do with those numbers. Employees, volunteers, we have a huge amount of contributors, lots and lots of research centers around the world that basically are universities doing full-time anonymity network research. So to understand Onion Services, so I'm mentioning Onion Services because a year and a half ago, we discovered that hidden services was kind of really bad for us in the press. And the journalists are just interested in this bad side of hidden services, and this is all they show. So we decided to move away from it and call them Onion Services. And it happened to be also that we're creating this next generation thing. So when I say Onion Services, it is hidden services, the same thing. To understand them, we need to understand how Tor works. So I'm assuming that you are basically familiar with the 3-hop thing in Tor, but I'm still going to explain it quickly. So Alice wants to connect to Bob. We have 7,000 relays in the network. All those relays are the ones with the small onion. And imagine all those 9 servers are the internet. And when Alice gets in, she picks a guard, then a middle, then an exit, then she exits to Bob. And in this case, when you exit, if Alice chooses an insecure protocol, well, the link is unencrypted when it exits. So this is why it's very important to understand that Tor is an anonymity network. It's not a secure network. And by that, it means that if you use an insecure protocol, you're still going to get, the exit's still going to see your content. Now, the exit doesn't know where Alice comes from. That is where you get the anonymity. So this guard context, this guard notion is very important here. So the entry point to the network is a guard. Let's remember that. Then the middle and the exit. In case of onion services, as we'll see later, there is no exit at all involved. And the reason is because onion services stay inside the network. So you can spawn a website, whatever it is, and then join the network, and then you'll be reachable only inside the network. You will never exit the network. So this guard, middle, let's keep that in mind. Some brief statistics, as I said, this is since 2011 up to 2017. We have many relays. So you can see this gap in 2015, at the end of 2015, this huge dent. So it happened to be during the Congress at CCC in Hamburg. Not me. And some people from Lizard Squad, maybe you heard of those, they decided that it was a good idea to show the world how good they are, and they spawned 1,000 relays from this Google Cloud app thing, whatever. And we quickly figured it out. We rejected them for the relay, and that was it. But they did brag during the weeks that they were able to take over the Tor network, but they actually didn't understand what it was. So that's what it then is. And the 2014 one, I believe it's the Artbleed. I'm not sure. I think it's around those times. This bandwidth thing, we're around 330 gigabit a second, and what is being used is around 100 gigabit seconds. So we still have some margin in the network. Okay, now I'm done. Now you know what Tor is and how it works, briefly. Onion services. So back in 2004, so it's been a while, it's been 13 years, the first commit was made in Tor 00.6. And it was hidden services. So at that time, Tor was under the EFF, so this is why you have this banner, tor.eff.org, and it was mostly experimental. So, but the point is that it's been a 13 years technology, if you will, and it's based on 16 character long addresses, so it's base 32. Here's an example of what an onion address looks like. I'm pretty sure you all seen one or know one. CNC, botnet CNC loves those, and they have those amazing properties that I think I have a slide about that. Client server either locations, everything stay inside the Tor network, and of course it's only TCP. There's no UDP, there's no other protocol. Tor is only TCP. Now, with onion services, you get interesting properties. So the self-authenticated, what it means is that if you have this onion address and you got it from a secure source, a secure channel, or whatever, and you know that this onion address was given by the right person who runs the service, when you reach the service, you're sure that you authenticated. You're sure that you reach the destination, and it is done with some fancy crypto. So it's very nice as long as you have the onion address. Oftentimes, it's giving the onion address to the other people, which is the problem. Now, it's end-to-end encrypted. So with onion addresses, for instance, you don't have to run an HTTPS server. You can just run an HTTP, and from the client to the server, it will be completely encrypted through the Tor circuits. Remember how Tor works in the normal case when you exit to get to Gmail. Now, the exit sees the connection to Gmail, and if it's unencrypted, sees the content. In the case of onion services, impossible. Isolation and not punching. In the NAT punching is one of the use cases that people use the most. So they basically run their onion services at home, an SSH, and the way onion services work is that it punches through NAT, and then you can connect to the services. You don't have to do any firewall fanciness or whatever. Limit the attack surface, of course, because it's a very narrow attack surface where there's only one port open, and you have to do this onion services dense through the Tor network. You cannot reach all the ports in the machine, and so on and so forth. And one of the last things that we've seen onion services being used around the world is censorship resistance. So we live here in Canada, which basically, instead of controlling the internet in some ways, they're just surveilling it. But there are countries that they're doing both, and when they do control, it means that if you get caught using Tor or you get caught using Facebook, well, you get some police to your door. In this case of censorship resistance, many countries, I mean, the list is very exhaustive, but Iran, Pakistan, China, and so on, so for Bangladesh, even Australia does that, they block Tor. So the way you want to reach your destination is to use onion address, because it's unblockable, you cannot censor it because it stays in the network. Now, bridge comes into play because you still need to reach the Tor network, but I'm not going to get into bridge, but still, the point is you cannot censor an onion address service. So back in 2015, we started to create statistics about what was happening in the network in terms of onion address. Right now, we have around 70 to 80% of all the relays reporting statistics of hidden services. There's a lot of research involved in how to collect those statistics, so they're privacy-preserving matter. And you can see right now there's around 60 to 50,000 unique onion address at all time. We have no idea what they're used for, but they're just there in the network. So that's a lot of services registering to the Tor network. Now, this is the traffic in megabit. And all those fluctuations, we have no idea what's going on. For instance, here, those peak, it could be some attackers or some researchers or new botnet. We have no idea. In this case, very little traffic, 1 gigabit a second, a little bit below that. Which means that the entire Tor network, as an onion service traffic, it's around 3% of traffic. So when you hear on the news that Tor is only used for bad guy through this onion address, through onion services to distribute whatever, it's actually very false because the traffic is extremely low. Now the question is that fraction, how much is used for bad and good? That is actually very impossible to know. That's an overview of what are hidden services. So in this case, we're going to see how it works because over time, those onion services are getting weaker, for instance. So I'm going to show you and explain to you some attacks and some problems we're having right now and to deal with them. But first, of course, I'm going to show you how hidden services works. So there's 6 steps. Basically, I broke down that in 6 steps. Imagine you have Alice, the client, wants to reach the service. So the first thing it's going to do is the server is going to start up and select 3 introduction points. Those introduction points are relays. Remember, there are 7,000 relays across the network. So randomly, the service will pick 3 relays and consider them introduction point. Now, I have that. Now, the service will create what we call a service descriptor. A service descriptor is a text file, basically a signed text file of which introduction point I've picked, how to reach them, and how to reach me, and some keys, some encryption keys, so we can have this nice end-to-end encryption. Now, this descriptor is going to be uploaded to a directory. Those directory, we call them HSDIR, Hidden Service Directory. Those directory, again, are relays. Every relays, if it's up for 96 hours, 96 hours of uptime minimum, becomes an HSDIR. And then the service takes this descriptor, uploads it to the directory. Now, Alice gets the onion address of the service, and then the first thing it's going to do, put that in Tor browser, for instance, and then the Tor daemon will ask the directory, what is the descriptor? I need this descriptor. Now, you may be asking yourself, how does Alice know which directory contains the descriptor? Because the service doesn't upload the descriptor to all 7,000 relays. It's only uploaded to 6. I have nice slides to explain to you this, because there's actually an attack that is being pulled every day in a Tor network due to a flaw in the design, but I need to explain this more thoroughly in the directory. So just keep in mind that Alice can know which directory the service is associated. And then, getting the descriptor, it knows where to reach the introduction point. And in the meantime, the client will also pick what we call a rendezvous point, which is also another relay. Introduction point, directory, rendezvous point. There's a lot of things there, but they all blend together at some point. Now, Alice connected to the one introduction point, which the service has a circuit. And now they can introduce, saying like, hey, I want to connect to you. So what the client Alice will do is send to the service through the introduction point where to connect to the rendezvous point. So come see me at the rendezvous point. And now service connect to the rendezvous point, Alice is connected to the rendezvous point, and this is how they actually splice the circuit, and then the traffic goes in. Now there's a reason why this dance is needed, and I'm not going to go through in the detail of the research about that, but the point is to keep anonymity and being reachable, and there's multiple amount of attacks that you can do if we didn't have this dense thing with the introduction point or rendezvous point. I'm gonna just show you a couple today, not the entire catalog, which also we're trying to fix. Now back to the directory. The reason why Alice knows which directory to get is because it's predictable. So here the first rectangle you see, it's descriptor ID. We call it descriptor ID. So remember the descriptor is the text file that the service publish and contains information how to connect. In this descriptor ID, it's basically an hash of the onion address, and then time period, descriptor cookie, and replica. Descriptor cookie, it's empty because it's for client authentication, so we're not going to talk about that. But then the time period and replica are known. So this time period thing is basically you know what's the number or the value tomorrow or in 2 years. So it creates a descriptor ID, and this descriptor ID is just base 16, and then it gives you a big string, and then this is how you pick the relay. You're going to pick the relay with the fingerprint closest to the descriptor ID. So it's basically a hash ring, like this. Descriptor ID number 1, and then you just pick the closest relay next to it, and this is where you upload your descriptor. And then this replica thing, it's 1 or 0, literally. And the reason is just to move away, kind of split the hash ring in some ways. So 6 directory. So it means the service has uploaded its descriptor to 6 directories, and now this is how it knows. And Alice can know which SSD because she can do the same calculation. Now this is problematic in many ways, and I'm going to show you why. As I said, 13 years, and crack started to form. For multiple reasons. At first, it'll be weak cryptography. This is supposed to be a super nice GIF with the guy and Operation Swordfish hacking, but whatever. So in Tor, since a year or 2 years ago, 02.024, and then we had 030, so maybe 6th version, every relay is talk with elliptic curve cryptography. ED 25519, if you're familiar with that. The only remaining RSA, weak RSA, is in Indian services. The identity key of the service, that's the onion address, is an RSA 124. So this is really bad, and we do know about that. And the second thing is the SHA-1. Tor still has SHA-1 here and there, but Indian services also rely on that. So obviously, if you want to do a rewrite for next generation, I'm going to get rid of that. So because of this weak cryptography and how old the design is, what we've started to see more and more is attackers running relays, and they become directory. So they get a lot of descriptor from different services. Remember, they have 50,000 services around the network. And then getting that descriptor, because of the weakness in the protocol, you can get the onion address in plain text in the descriptor. So descriptor looks like this, rendezvous service descriptor, some yada, yada, yada. And then here is the permanent key, which is the identity key, which is the RSA 124 we talked about. And this becomes your onion address. So which means that people sit on the network and can list and harvest onion addresses. And what they do is that they get those onion addresses, they crawl them, and then sell the data to some whatever corporation, law enforcement, or military. We've been blocking those people for a year now. So we have some way to detect that, which is a very clever system that we actually keep hidden because we don't want people to understand and just go around it. I wonder if I have a slide about that. I think I might have a graph showing how many bad relays we remove. But it's a non-stop issue for us. Now, there are multiple problems with letting people to know onion addresses. So by design, hidden services or onion services are supposed to be hidden. So if you want to run an onion service, you should have this assurance that if you don't give out the onion address, nobody will discover it, nor be able to reach it. And remember, with onion services, you only need the onion address to reach it. So this big problem, and not only that, but there's a lot of people doing it. Now this is the directory predictability I was talking about. Oh, I forgot that, this amazing slide. So this time period thing, you have invariant, this time period thing, so that means in 2 years, I know where to go, where the descriptor will be. What it creates is an attack on, that we've been seeing and we've been blocking for the last couple of months because we have a new detection that's been rolling out. So what you're going to do is camp at the right place when you know the descriptor is going to come in. So let's say you want to camp those, become the HSDR of a specific onion address. Let's say WikiLeaks, for instance. So you want to know, so you take the onion address of WikiLeaks, then we do this calculation, the onion address, the time period, and then you know it takes you 96 hours to have the HSDR flag. So you put in the 96-hour time period, you do some math, and you know exactly what descriptor ID is going to be in 5 days, 96 hours. And then you brute force your fingerprint to camp at the right place, and you become this HSDR number 2. So which means that every time WikiLeaks service will publish its descriptor, you will receive it. Now this opens up an all new set of attacks because you have a circuit. You're able to have a circuit from the service of WikiLeaks to your relay, but it's still a circuit of 3 hops. So you still have anonymity, but then there's other issues. Same thing, camping. So you inject yourself. The red thing is you inject yourself. Oh, wow. Okay, this is out of order. This is how many relays we block every day. All circles, the red ones are 100 and more. So since 2015 up to 2017, we're constantly monitoring the network, and we're finding a shit ton of bad relays trying to do this thing. So let me explain to you, coming back to the directory. Imagine you just camped as an HSDR. So you computed the descriptor ID in 5 days. You brute force your identity key so it matches the descriptor ID in 5 days. And then you start up your relay. You wait 96 hours, and you get your HSDR flag, and then, perfect, WikiLeaks is going to upload your descriptor to you. So imagine Alice here is WikiLeaks. Now, the second thing you want to do is, and we've seen people doing that, is run guards. So guards, remember, is the entry point of a client and a service. So you run, let's say, 10 relays, and you let them simmer for months, and then they become guard after some time period. But then you have your HS Direct3. So this is a client de-anonymization attack. So that means if you pull off this attack, you will know everyone that is connecting to WikiLeaks. In this case, this is how it works. We start at 1:37 UTC. Your guard gets a connection from a client. And then 2 seconds later, your Direct3 gets a request for the WikiLeaks onion. All the red ones, you control. So you have this time thing. Okay, is this a hidden service connection? I'm not sure. Remember, those are circuits. Now, 1 second later, this circuit gets killed. Because what happens is the Direct3, and this is how Tor works, the Direct3 sends you back the descriptor and then kills the circuit. So then, 1 second later, the circuit gets killed. Then what happens at your guard is that 2 more circuits gets created in the same seconds. One going to the IP, the introduction point, and one going to your rendezvous points that you picked. Now, once you introduce yourself, this is a very short-term circuit. So 2 seconds later, it killed the circuits. So you have this nice timing pattern going on that you can see at the guard. And remember, you control the guard. And then there's a lot of traffic going through the third circuits. So to summarize, you see this timing attack that you can just follow, and then you know that this client visited WikiLeaks or requested it. So this is problematic. And one of the reasons it's problematic is because few years ago, we switch in Tor. I'm not touching it. We switch in Tor. So usually you used to pick a guard, a different guard for every circuit, and keep it for maybe a few hours. Now, it turns out some clever fellow in some research lab was able to de-anonymize everyone with that. And the reason would be to run a guard and make you connect the service 6,000 times until you pick his guard, and then it's job done. I just de-anonymize your service. So for that reason, this rotation of guard has been cramped up to 3 months. So every client that you have here, you keep your guard for 3 months. So that means if you're lucky enough to have the guard of clients going to WikiLeaks, you're going to see everything. Not the content, of course, just the connection we're talking about. So that is one problem we're trying to solve. I'm going to explain how we're trying to solve it later. All right, so this is the second attack. Now, let's say you want to discover, and oftentimes this is what people want, discover the guard of the service. So you don't care that 10,000 people are going to WikiLeaks. You do care where WikiLeaks servers are, because you want to take them down. So this guard discovery attack is based on 2 issues we have. Well, 2, maybe more, but let's say just 2 for now. The first one is that as a client, I can make the service create circuits. And how it's done is because as a client, I choose the rendezvous point. So I'm going to tell the service, go to that rendezvous point, 1, go to that rendezvous point 2, 3, 4, 5. So that means the service creates 5, 6, 7 circuits. So this is very nice because this gives you this kind of side channel attack at the guard that you can see and you can basically know what's going on. And then the second thing is hidden services circuits are very distinctive. They have a set of cells being sent, and then the circuits dies, as we saw with the timing of the client anonymization. But on the service side also, because if you run a service website, for instance, and then where your website is a specific size, it's going to send a specific amount of cells. So at the guard, I can count those, but not even at the guard. I can also count those at the middle node, the entire Tor circuits. So how it works. So this guard discovery attack, we don't really know if some people are pulling enough right now, but we have our doubts because in the last, I would say 4 or 5 months, we've seen more and more relays that are not exit being taken down by law enforcement. So we don't really understand what's going on. It's maybe some just paranoia, or they have no idea what they're doing, or someone figured something out. So in this case, imagine you only need to run the middle node. And middle node are rotating constantly. Remember, your guard, you pick it for 3 months. So you're the service, you're WikiLeaks, you have a guard for 3 months, but then you're going to pick middle nodes to connect to multiple rendezvous points. So this middle node is very easy, low bandwidth. As long as it's running, you can get picked. So you just run that. Sorry. And then what you want to do here is discover the guard, because the chance that you are the guard is very low because it rotates only 3 months. So there's like 3,000 or 4,000 of those. So you just want to discover the guard, then take down the guard, and go to the ISP, get some net flows, and you know everyone that connected. You know where the service is. So in the middle, as the middle relay, you can control an RP, a rendezvous point in the middle. Then your client, you make the service connect constantly to this RP, and at some point it's going to pick your middle node as in the circuit. And you know the pattern of cells going through the RP because you can control the data going in and out to the service. If it's a website, you can do like 3 or 4 double you get with a specific time rate, and you know how many cells, and then you just count that at the middle, and then boom, you know that your middle is not connecting to your rendezvous point, so that means the inbound connection, it must be the guard. In this case, because there are 2 middles, so which one are you? But you know, because you control the RP. And thus, if there's no inbound connection, if there's no outbound connection to your RP, you know you have the guard. This is a very efficient attack. Very low resource. You just need few relays, and you just wait, and at some point, you just pick it up. If you remember 2015, maybe some of you remember because I'm pretty sure a lot of people here went to Black Hat. There was this controversy about those two researchers going to Black Hat and having this amazing Tor talk. Someone remembers that? No, man. 2 years ago. And it was pulled off completely 2 weeks before Black Hat. Nobody knew what happened, whatever. What actually happens, and we made a blog post about it, is that those were two researchers from CMU, the Carnegie Mellon, and for 6 months, they pull off this kind of attack in the network, but with some more nasty stuff, which was side channel attack inside Tor, which I'm not going to get into because it's much more complicated, but still they put it off. Now there's a downside to that, because they didn't target one specific onion address, they targeted every onion address on the network. And when you have governments like NSA or whatever that records encrypted traffic, well then this 6 months attack, you can just replay the entire thing if you got the packets passively, and then de-anonymize a lot of people. So following that, we of course fixed the issue and created a research board, which was basically, if you're doing research in Tor, contact us and don't do it on the real network because it put people at risk, literally. And this kind of attacks, we think that it's getting pulled off more and more and more. Thus, this thing is very important. Next generation onion services. For people that are very curious, we have this Tor specification Git repository, and it's proposal 224. It's a huge proposal, and it's basically try to fix everything. Now, first of all, better cryptography. That is for sure. Tor right now is using massively ED25519 in Curve, but we're also using KeyCac, which is the SHA-3, more and more. So we're dumping this entire RSA thing. It's really nice because elliptic curve basically fits on 32 bytes, which RSA keys are humongous. Now the new addresses, that's a big thing, that's a problem we're gonna have. And I'm not even kidding here. 16 characters, we're gonna go to 54, which is, in a nutshell, your ED25519 public key with some 2 bytes of checksum at the end. So typing this is gonna be a problem. We do have UX and UI people in Tor that are trying to come up with ways, like pet names and registration, and just throwing ideas out there so we can make Tor browser usable with those kind of address. But it turns out someone made some kind of research with focus group. Nobody actually types onion address. Nobody remembers them. So maybe it won't be useful to have a nice UI, I don't know. But this is the reality of things. Now, going back to the director predictability problem, how do we fix that, right? We need something that varies in the descriptor ID that both the service and Alice can compute, but it's still something that they cannot fetch, because if they fetch it, it becomes an invariant, so what is it? So what we created, and it took us a year of last year to create a shared randomness. So behold, our 8 directory authorities. In Tor, I didn't talk about that, but how do you know where to connect? How do you know where the relays are? It's done through 8 trusted entities, which we call them directory authorities. You have all their names, it's their real names, and they're across the world. I think it's 50% in the US and 50% in Europe right now. And run by trusted people we know. We met in person and so on and so forth. And so every hour, they create what we call a consensus. The consensus is a set of all the relays. So this is how you know where to go. This is how you know as a client, when you start, you contact one of those, and then you get the consensus, and then you know how to do your circuits. So every 24 hours since 6 months ago, all those directory 30 create a shared randomness, a shared random value, sorry. What it means is that we use a very simple system of commit and reveal. So for the first 12 hours, they're gonna take a shared random value, hash it, and publish it in their vote, because they all vote in a consensus. That's another topic. So they publish it. So all 7 other directory 30s do the same, and then they get all those values, but they're hashed. And then after 12 hours, the last 12 hours, they do what we call reveal. So they reveal the value that corresponds to the hash. Now that creates a thing where they all have 8 hashes, they sort them, and then hash the entire thing and create a shared random value. And in the end, all 8 come down with the same value. I mean, I can go on for hours on this because it took us a year to pull it off, but it's something is being done. And because of that, every 24-hour consensus has a random value. So it's kind of the NIST beacon of random, just without backdoors. So it's kind of really nice. And we know that other applications are actually using it that are not linked to Tor at all. So what it creates, then you cannot camp on the HSDIR because every 24 hours of this new value, and you get the HSDIR flag after 96 hours. So you cannot predict where the descriptor is going to be. So we just neutralize the camping attack. Now I'm going to switch to guard. We've seen a bunch of problems with guards. This is the current design. Onion services, I'm going to connect to a guard, then a middle, another middle, and a rendezvous point. And there's a reason why you do 2 middle here, because remember, one Tor circuit is 3 ops, but this thing is 4 ops. And the reason is because in anonymity research, you'd never want to extend to a relay that you didn't pick. So the rendezvous point, the service didn't pick it. So because of that, it adds a third up. If you have 3 ops, you have anonymity. So 1, 2, 3 to the rendezvous point. Now we've seen this attack with the middle being bad. So how do we try to fix this? Now this gets a bit more complicated. We call this a vanguard proposal. And remember, the first guard is 3 months. Now 3 months is a whole lot of time for law enforcement or whoever to find your guard and then go to the ISP or the hosting provider and make them turn on the NetFlow records or whatnot. So what we went through is saying, okay, we're going to have a set of different guards. Those are called the vanguards. And then if you look at the bottom, so it's all no intersection between those sets, and they rotate at different time. So 3 months, 11 days, and 12 hours. And the reason is of this, we went through a lot of politics and how law enforcement works and so on in different countries. And we do think that around 11 days, it's kind of tough for law enforcement to actually find it and then get a subpoena and go get it, and then go back to the other guard and then subpoena it again, and 12 hours as well. So we came up with this scheme that we think would be better. Now, the other thing with that scheme is that to put yourself in one of the guards set for the DIN service you're looking for, it's going to be much more difficult. Of course, you can become the primary guard, but if you do, as WikiLeaks service, I'm fucked anyway. So this is a Vanguard proposal. This thing, we're still working on it right now. It's kind of very complicated. There's a lot of anonymity issues, and it needs a lot of research. But we're getting there. We're getting there. So I've talked, there's one thing I forgot to mention here. So remember, descriptors have the onion address in plain text. So that means we have this harvesting situation, harvesting onion addresses situation. So how do we fix that? It's very simple. It's make the descriptor encrypted so the hidden service doesn't know what's the content. And we created that with this very nice blinded key scheme, which I do not understand. But there's a lot of research paper being done that have been done, and we implemented that. We have really good cryptographers that did that. And the client and the service creates a key based on the time, and then derive from the onion address a key, which we call a blinded key. And no matter how many blinded keys you see, you cannot go back to the identity key. But the blinded key, the difference is the blinded key can be associated with the onion address, so the identity key, if you know it. This means if client and service are the only one who can decrypt the descriptor, which means the directory doesn't see the onion address. So we fixed that way. So you won't be able to harvest onion address. You won't be able to camp in the hash ring as an HSDIR. You won't be able to pull off this middle attack as guard relays. We have better cryptography. And this new thing also, which is called single onion services, it has nothing to do with any attacks, but it's really nice. Oftentimes services don't need anonymity. And what I mean by that is if you run Facebook servers, we all know where the Facebook servers are, and they don't care. They tell the world where they are. So you can remove this entire anonymity 3-up circuits from the service to the rendezvous point. So this is what we did with single onion service. You can set up your service as a single onion, and you lose anonymity on the service side, which makes this thing way faster because now it's only 3 ups and then the service. For instance, Facebook, 2005, I think, they fired up an onion address. So you can reach Facebook nowadays through their onion service. And they have millions of people connecting to that. And they were at the forefront of beta testing this feature. And right now, they are running single onion service. So you'd only do 4 ups to Facebook instead of 6. I'm almost done. Progress, where we are. So shared random is an 029 stable. Just a reference point, 2 weeks ago, I think, we released stable of 030. So 029, 030. So shared random is 029, and this nice line, shared random current value, is what it looks like in the consensus. So if you fetch the consensus, this is how the shared random value looks like. In every 24 hours, it changes. The directory system is all coded, it's all integrated, it's been released in 030. Service implementation was the biggest piece of effort. This is, what you're seeing right now is a 3-year engineering effort, and we're coming to an end by the end of the year. The service implementation thing is a humongous effort. It took us a lot of time, but we're there. Right now, we're stress testing this entire thing. It's going to be in 032, which will be stable by December. The reason it's not in 031 is because on Monday it was feature freeze, and I was here, so couldn't release that thing in 031. Then the final one is the client implementation, and once the client implementation is done, we have all the pieces, and we hope it works. So we're aiming for December 15th. This new written service generation will live in parallel with the current system. So the current system, the next generation, for years, they're going to be in parallel, so it's going to work. And the reason is that we went through many discussion with the community, and killing the legacy system would be a disaster. Everyone will freak out. So for many years, there's going to be this transition path. I think I'm pretty done. Use Tor, and this is about onion services.